Chapter 1, Relations and Functions, Class Number 1. The concept of the term relation in mathematics is similar to the meaning relation in English language, according to which two objects are related if there is a recognizable connection or link between them. The important concept to learn is understanding that link or relation. Let A be the set of students of class 12 of a school, and B be the set of students of class 11 of the same school. Then some of the examples of relations from A to B are provided in the below box. If A, B belongs to R, we say that A is related to B under the relation R, and we write as A or B. A relation in a set A is a subset of A cross A. The empty set that is null and a set with elements with A cross A are two extreme examples of a relation. Consider a set A with four elements 1, 2, 3, and 4. Consider a relation R with two elements A and B. The relation R defines two elements such that A minus B is equal to 10. This will be a null set as no pair of A and B be defined where A minus B is equal to 10. These two examples lead us to the following definitions. Both the empty and universal relations are called as trivial relations. Example, let A be the set of all students in a boys' school. Show that the relation R in A given by R is equal to AB, where A is a sister of B is an empty relation, and the relation R dash, where difference of heights between A and B is less than 3 meters, is an universal relation. One of the most important relations which plays a significant role in mathematics is an equivalence relation. To study equivalence relation, we first consider three types of relations, namely reflexive, symmetric, and transitive. Relation R in set A is called reflexive if A, comma, A belongs to the relation R for every element A in the set. If A1, A2 belonging to R also implies that A2, A1 belongs to R, then we call the relation symmetric. Relation Let T be the set of all triangles in a plane with RA relation in T given by R is equal to T1, T2, such that T1 is congruent to T2. Show that R is an equivalence relation. Finally, T1, T2 belonging to R implies they are congruent to each other. Similarly, T2 and T3 belonging to R implies they are congruent to each other. Hence, T1 and T3 are also congruent to each other, implying it is a transitive and an equivalence relation as well. Let L be the set of all lines in a plane and R be the relation. in L defined as R is equal to L1, L2, such that L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. Show that the relation R in the set C of integers given by R is equal to A, B, where 2 divided a minus B is an equivalence relation. R is reflexive as 2 divides A minus A for all A that belongs to Z. If 2 divides A minus B, then 2 will also divide B minus A. Hence, R is symmetric. The same logic will not hold true if A, B belong to set of natural numbers. R is a transitive relation because of this logic, and hence R is an equivalence relation. Let R be the relation defined in set A, where R is a relation between A, B, such that both A, B are either odd or even. Show that A is an equivalence relation. Additionally, go through the second part of the question. A is reflexive because if A is either odd or even, so will be A. A is symmetric because if A, B both are odd or even, so will be B. A. R is also transitive based on the logic provided in this slide. Let R be a relation in set A such that R is defined in xy as 3x minus y is equal to 0. Determine whether R is reflexive, symmetric, or transitive. R is not reflexive as putting y is equal to x in the above equation, we get x is equal to 3x, which is impossible. X is neither symmetric because after interchanging x and y, we reach at x is equal to 3y, which cannot be true. Putting y is equal to 3x and z is equal to 3y, we reach at z is equal to 9x, which is not equal to relation R. A relation R in the set N of natural numbers is defined such that xy is in R and y is equal to x plus 5 and x is less than 4. Determine whether the equation is reflexive, symmetric, or transitive. R is neither symmetric or reflexive because of the given logic as indicated. R is transitive as there are no two pairs in the roster form which has the values x, y, and yz. Relation R in the set. A such xy is in R and y is divisible by x. Determine the relation is reflexive, symmetric, or transitive. R is reflexive as all the pairs of elements in the set is present in the relation. R is not symmetric as 2, 4 belongs to R, but 4, 2 does not belong to R. Hence, R is a transitive relation. Show that the relation R in the set R of real numbers defined as R is equal to A, B such that A is less than equal to B, square is neither reflexive nor symmetric nor transitive. R is not reflexive. If we put B equals A in the relation R, then A needs to be less than a square, which is not true for any positive number less than 1. If we take A equals 1 and B equals 2, then A comma B is in relation R, but B comma A is not in relation R. Hence, R is not symmetric. Show that the relation R in the set R of real numbers defined as R is equal to A, B such that A is less than equal to B, square is neither reflexive nor symmetric nor transitive. If we take A equals 10 and B equals 4, then A, B are in R as B square is greater than or equal to A. If we take C equals 2, then B, C is in R as C square is greater than equal to B. However, A and C, which is 10 and 2 respectively, are not in R as C square is not greater than equal to A. Hence, R is not transitive. Check whether the relation R defined in the given set, where A, B is in R and B is equal to A plus 1 is reflexive, symmetric, or transitive. From the roster form of the relation R, we see that 1 comma 1 and 2 comma 2 is not in R, and hence R is not reflexive. R is not symmetric because while 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. R is not transitive because while 1 comma 2 is in R and 2 comma 3 is in R, whereas 1 comma 3 is not in R. Show that the relation R in the set A, where AB is in R, such that mod of AB is even is an equivalence relation. For all A that belongs to A, mod of A minus A is equal to 0, which is even. Hence A belongs to R, and hence R is reflexive. If mod of A minus B is even, mod of B minus A should also be even, and hence R is symmetric. Since A minus B is even and B minus C is even, adding two even numbers is even. Hence, A minus C is also even and A minus C is in R, which implies that R is transitive as well. Additionally, show that all elements of a set with elements 1, 3, 5 are related to each other, and all elements of a set with elements 2, 4 are related to each other, but no elements of these two sets are related to each other. A set with elements 1, 3, 5 have all odd numbers as elements. Since the difference of two odd numbers is even, all the elements of the set is in R. Similarly, a set with elements 2, 4 will be in R. Since difference of two even numbers is even, show that the relation R in set A as given in the question is an equivalence relation. Let small a be an element of the set capital A. Putting B equals A in the relation, we get R is equal to m mod A minus A, which is 0. Since 0 can be said to be multiple of 4, R is reflexive. Let small b be elements of set A where A, B belongs to R. Mod of A minus B is equal to mod of B minus A, and hence the relation is symmetric. Show that the relation R in set A, as given in the question, is an equivalence relation. Let small small c be elements of set A where A, B, C belongs to R. Since A, B belongs to R, mod of A minus B is a multiple of 4. Let M be an integer such that mod of A minus B is equal to 4M. Hence, from the above, A minus B should be equal to plus or minus 4M. Similarly, B minus C may be equal to plus or minus 4N, where N is an integer. Mod of a minus c is equals to 4 times m plus n, which is again a multiple of 4, since m and n are integers. Hence, R is a transitive and an equivalence relation. End of class 1 on functions and relations.